Hi there, I'm Hao. This is just another video of me solving random code problem. So let's begin. So given two integer arrays, um, Inorder and Postorder, where Inorder is the inner traversal of the binary tree, and the Postorder will be the post-order traversal of the binary tree. Construct the tree and return the binary tree. Okay. So what is Inorder? Inorder means we process the roots right in the middle. So we process the left, the root, and then the right, right? So right left, so it's 9, right, the root, so 3, and then the right, right, for the right, we go to the root, right, go to the left, first, so 15, and then the root is 20, and then the right is 7, right, which match up with what we have here, 9, 3, 15, 27, right, post order, mean we process the root last, right, which be left, right, and then the left, right, and then the root, right. So left, which is 9, right? And then right, left, right, 7, and then the root, so 20, right? So we finished the left, the right, so now the root, 3. So 9, 15, 7, 20, and 3, right? So that is what it meant by in order and post order. So how can we construct the tree from this? So because we know that the in order, right? For the in order, we know that it is left, right, root, and then the right. So if we know where the root is, then we know that everything on the left side will be on the left subtree, and everything on the right side will belong to the right subtree, right? So let's say we take 3, we look at 3, right? 3 is as the root here, right? So we know that the root is here, so everything on the left. So let me make it bigger here. So 9, 3, 15, 20, and 7, right? So if 3 is the root here, right? So we know that everything to the left, right, is on the left subtree, and everything on the right, right, will be on the right subtree. Okay, so doing it this way, we can construct the binary tree. We can use the post order as the root. We can use the post order to build out the root. So because it is post order, if we look at this in reverse order, right? It is 3, 20, 7, 15, and 9, right? So 3, 20, 7, 15, and 9, right? So look like it's process the root first, right? And then the right, and then the left, right? Right. Because if it is post order, remember it will be left, right, and then root, right? But if we look at it in reverse order, right, it would be root, right, left, right? So we can reconstruct the tree using this strategy. Okay, so let me make some space here. It is 9, 15, 7, 20, and 3, right? So let's say we are looking at this is our so remember this is root left and root right and left, root right and left, right? It is if it is in reverse order, right? So we have our post order array, so 9, 15, 7, 20, and 3, right? We'll be looking in reverse order, right? Which is right, root right, left. Remember? So we can have our let's say this is post order, right? Index. we can start at the last element here and going backward, right? And we can have the left and the right here as the bow of the tree, right? So we can start out by building the roots, right? We can process the root first, which is 3, right? So after we process 3, we want to increment our index to 20, okay? So the bow at the root is what? The bow as the root is gonna be let me write out the index here so it is easier to see. So this is from 0 to 4, right? 0 to 4. But if we go left, the lower bow is the same, right? But the upper bow become 1, right? Uh, sorry, the upper bow become, wait, this is the wrong array. We need to look at the in-order array. My bad there. So in-order array is, oh, in fact, it is the in-order array, right? Yeah, never mind. Yeah, it is an in-order array. Okay, so the 3 should be here instead, right? 3, 9, 3, 15, 20, and 7. Yep. Okay, so we know that the root is here, right? The root is here, which means everything on the left will belong to the left subtree, right? So when we go left, the bow become the index of the root, right? -1, so 0, 0. So that is whatever we have left uh, on the left subtree, right? Which is 9. Okay. Um, if we go right, right, the uh the bow, the upper bow stay the same, right? But the lower bow become the index at the root +1, right? So 1 plus 1 is 2, right? So this part right here, okay? And remember that we need to go in the correct order here, root, right, and left, because we process it in reverse order, right? Okay, so now we look at the right first, right? So we continue to process the root, which is 20. Let me change color here, 20. Okay, uh, if we go to the right, so after we process the 20, don't forget to decrement the post order index, right? And we need to go to the right first. If we go to the right first, what happened? So we see the root is here, right? The root is here at index 3, right? And the bow is from 2 to 4, don't forget. From 2 to 4, so only this part, right? 2 to 4. So the upper bow stay the same, which is 4. The lower bow become the root index, right? +1. So 3 plus 1 is 4 and 4, right? So now we process the root again, which is 7. Let me change color here, 7, right? So we update we decrement the post order index to here, right? And now we go to the right again, right? And the bows become, so the root is at 7, right? So the lower bow become the index of the root +1, so 5 and 4. So now they are overlap, right? So in base case, if the left is greater than the right, we can just return no, right? So now we finish processing the left side, actually the right side, we can go to the left here, right? So if we go left, the lower bow stay the same, but upper bow become the root, right? Which is 7 here, 4, index 4 -1 is 3. Because left is greater than 3, sorry, left is greater than right, we just return no, right? So now we finish processing the right, we go to the left here, right? If we go left, uh, the lower bow stay the same, upper bow become the index of the root -1, right? So the index of the root 20 is index 3 right here. right? -1 is 2. Okay, so that is still valid. So we process the root 20, right? Root right, left, remember? So we finish the left, right? We finished processing, processing the, we finished processing the root, right? We go to the right, now we go to the left, okay? And now we need to go to the right first, right? And if we go to the right, it's just gonna be, we know, right? Because we are out of bound here. This become 2, sorry, it just become 3 and 2, right? You can just return no, right? And we can go to the left, it's become 2 and 1, right? Which also make us return no here, because left is greater than right, which is not a valid tree. Okay, so now we finish the root, right? We finish the right. So now we can go to the left here. So we can process the, oh yes, when we process the root 15, right? We have to also decrement the post-order index. Okay. So now we process the root again. So 9, right? We decrement the index again. So now it is our bound. We can to leave the right. It's become 1, 0. It become 0 -1, right? So this our bound. So we just return no. And then we return back up, right? So we are done now. We can just return the root of the tree, right? And this look exactly like that, right? Now 3, 9, 20, 16, 7. So we have successfully beat out the tree here, right? So again, the key here is to use the in-order array to differentiate between the subtree, right? Because the in-order array process the root in the middle, right? So which means everything on the left of the root, right, will be in the left subtree, and everything on the right of the root will be in the right subtree. So we can use the index as the interval, right, to separate out the different subtree to know where we are out of bound, right? And then we have to use the in-order, right, to set the interval for the subtree, and then we need to use the post-order to process the root to actually build the tree, right? The post-order is the one that is actually building the tree here, right? So post-order, we know that the post-order process the left, right, the right, and then the root first, left, right, and root right, last, right? Um, but we want to process the root first in this case, right? Before we going down the tree, right? Because okay, the thing is that we need to pass in the root, right? Um, as we iterating down the tree, right? So that we know where's the left and the right subtree, right? So that we want to process the root first. So that's why we look at it in reverse order, right? So that's why we can process the root first here, right? Because we want to pass down the root as we iterating down the tree. We traverse down the tree, right? And if we look at in reverse order, uh, the order gonna be flipped by root right and left. So instead of going root left right, we have to go to the right first, or go to the left. So that is how post order work, right? We can always process the root first, right? If we process the root first, it is important, right? If we process the root first, then we know where the root is, right? If we know where the root is, we can look at up the index in the in-order array and okay, set the interval, right? Where's the left and where's the right? So for example, just for example, if we use pre-order array, if we use pre-order instead of post-order, right? What does it mean? It means that we are having a root, right? Left and right, right? So in that case, we can just look at it in this direction, right? And we have to look at the left first before the right, right? Um, okay, so that's pretty much it. One more thing I want to mention is that how do we gonna so um so yes, index of, right? How do we gonna look up the index of the root? We need to look at the index of the root, right, to set the interval. So how can we do that, right? Because looking up the index is on, right? Because we need to search through the array, and we need to do it. We need to look at the node, every single node to build the tree, and if we have to look up the root like every time we traverse down, we see that it's OS we are in time, right? So how can we do this? We can keep track of the index, right, of the root. Sorry, of the node, right? Before we even building the tree. So in that case, we can look up in constant time, right? All right. So let code this up. So first thing first, we need to have a hash map, right? Or keep track of the index, the value to index, right? And then we can loop through the inorder, right? Inorder array, inorder dot for each num, it's val and index, right? Value to index of val equal to r. Right? Okay. And then we need to return view the tree, right? We're gonna start out at what? We're gonna start out at the 2n, right? So remember we start out at left and right, right? The 2n at index 0 and the length -1, right? Just a quick reminder there. So we did this in order at length -1, okay? And we need to have also have our post order index, remember? Post order uh, post order index equal to also length -1. We need to look at it in the reverse order, right? Because u equal to left and right, right? Right. So if left is greater than right, we just return no. Right? You have to calculate the root value, which is the post order at. So now we need to process the root first, right? And to process the root, we need to know the value of the root, which is the current value we are looking at the post order index, right? Post order index. So after we process the root, right, we need to determine the post order index. The root equals to new tree node, right? Passing in the root value, the left and the right. So we can just do it like separately. And we want to return the root at the end. Okay. So we can do root at left here equals something, right? And root at right equals something, right? So remember, we need to process the root first, right? And then the right, and then the left in this correct order. The view, right? And then view. Okay. So if we go to the right, up about stay the same, right? Which is the right. If we go to the left, um, the lower about stay the same. Okay. So the lower about stay the same, but up about become um the index of the root -1, right? So value to index at the root, which is the root value here, -1. And then if we go right, upper bound stay the same, but the lower bound become the value of the root index. Sorry, it become the index of the root value, right? +1. Root value +1. root index equal to value to index root value root index. Okay, that is clear. And yeah, that's pretty much it. Accept it, and thank you for watching.